All right, so let's start. My plan for today is continue on bulk boundary coupling. So we had these questions that I laid out last time, and you learned about quite simple examples, and especially what then the role of bulk boundary coupling is in simple terms. You also saw that the eigenvalue problem that you find when you solve a system that has a coupling between a surface and a bulk is more intricate than the eigenvalue problem that is for a simple 1D or bulk geometry alone. Now today I would like to study the linear stability analysis. So we're going to ask, given a homogeneous steady state, under what conditions is this homogeneous steady state unstable for a simple geometry? And this simple geometry is the one that we studied also here. So our simple geometry is a one-dimensional bulk geometry where the membrane is a line and the bulk is a two-dimensional volume. And I'll do this for a two-component system to illustrate how things work out. And then we'll move into real-life problems where we study the min protein system that gave rise to these beautiful oscillations that you saw here. Right, so we're really going to then dig into how we formulate a diffusion reaction model for such a biologically relevant system for all the components and with the bulk boundary coupling. And you'll see it will all fall into place because we have the basic building blocks available, which is the conceptual framework and how bulk boundary coupling works. All right, so let's go on the board and do the linear stability analysis for the two-component system. For a two-component system in what we called a box geometry. So our setup is that we do have a direction Z that defines the direction into the cytosol, and we have the direction X that indicates our membrane coordinate. So the concentrations that we're going to have is the bulk concentration as a function of X, Z, and time. And we have the membrane concentration as a function of X and time. We will have an equation of motion in the bulk, which is dTc of all these variables. And we will assume that for simplicity, there is only diffusion in the bulk, no reactivation by nucleotide exchange. So we just have one component, just the bulk component. And then I need to write the differential operator in bulk explicitly. And that's simple because it's just the Laplacian in bulk. That's the sum of a second derivative along the membrane and orthogonal to it. Good. The dynamics on the membrane, that is one which is with a different diffusion coefficient. So I have here dTm, and now let me omit the corresponding arguments of that. This is diffusion on the membrane, and now I need the Laplacian on the membrane. That's simple here because I'm just looking at a flat one-dimensional landscape. So this is just dx squared If I were to look at something more complicated like a sphere or a cylinder or other kind of geometries, then of course I need the Laplace-Beltrami operator for that particular surface. So here we just use the flat 1D geometry, which means this is dx squared m. And then, as usual, we do have a reaction term, which is the membrane concentration in full. And now I write it out because here there is a particular feature. What enters here in the reaction term is the concentration of the cytosolic component right at the membrane, so at z equal to 0. In order to be complete, I need boundary conditions. There are a few which are kind of trivial, which is the no flux boundary conditions. So when I'm here in a domain that goes from 0 to L, a box, then at the right and left end, I want the system to be closed. So I need no flux boundary condition, meaning that the diffusive currents of C at x equals 0 and L is 0. And I also want a boundary condition here at the top. So the system has a height h. And at the top, I also want the system to be closed. So that means then dz of C at z equal to h, that also needs to be 0. For the membrane, because it lives only on the membrane, I have then dxm at the two ends, 0 and L, also to be 0. Okay, this is, so to say, the trivial type of boundary condition. The more important one are the Robin or reactive boundary conditions. These reactive boundary conditions give us a balance of diffusive and reactive currents here right at the membrane. And as we discussed before, there is a diffusive flux and there is a reactive flux right here. Right? The reactive flux feeds the diffusive flux, and they have to be the same, otherwise I would gain or lose particles. So the way I write this is that a flux by diffusion into the cytosol right at the membrane, that's our diffusive flux. This diffusive flux needs to be equal to the corresponding reactive flux, right? And this reactive flux is now one where I attach things to the membrane. So it means I'm losing it from the cytosol, so I have to have the corresponding negative of the attachment flux that I have here in the reaction term. We had this already in our last lecture. So this is M and C again at the location of the membrane. Good. Those are the, that's the setup. There is, and that's the reactive flux. There's one more aspect that we need to consider, which is quite important. There is total mass conservation. So that means if I'm looking at my system and I'm integrating over all densities on the membrane, and I'm integrating over all the density in the cytosol, I need to get the total mass. So let's do that. let's integrate over our box from left to right. Then I have here the total protein mass that comes from the membrane component. And when I want to add the mass that's in the cytosolic component, I have to additionally integrate over the z coordinate, c of x and z and t. And that's then the total volume, L times H, times the total density n bar of proteins that you have in your system. Good, now we have a setup. Now we have the equations, we have the boundary conditions, and we have the fact that we have total mass conservation. To set up now linear stability analysis, I need to know what is the corresponding homogeneous steady state around which I will do my perturbation. So let's look at this first. Let's look at what is the homogeneous steady state. So let's call this HSS. There's a few conditions that you can easily read off here from this board. Right? Homogeneous steady state means that dTc is 0 and dTm is 0. That means the right-hand side is 0 here. And I can use that to write then the corresponding equations. Now, usually you would say the homogeneous steady state is one where all the concentrations are constant. C is constant and M is constant. That's not quite true here. We still will have that M of x and t is a constant value uniform over the whole box from left to right, but I'm no longer guaranteed to have a density profile in the z direction that's constant. This can, in general, be a function of z, right? This could be what I have as steady state concentrations in the cytosolic component and in the membrane component. Good, now let's use that. So we do have dx of c is 0. That means our steady state condition reads dz squared of c equals to 0. So we have dc, dz squared of c star of z is equal to 0. Because we have no flux boundary conditions, I can integrate that relation here once, and the integration constant is 0 because there's no flux at the boundaries. So we have from that dz star of z equals to 0. Right, and that means now that our c star of z, if it depends on the z coordinate in the bulk, it can be at best a linear function, right? This is the solution of such a equation. But we have here another boundary condition, which is this one here. See that at the ceiling we have to have also no flux, and accounting for that, the only solution we have in our case, so no flux at z equal to h, then implies that our c star of z is again just a homogeneous uniform steady state, no profile in the z direction. As said, this is not necessarily the case in all the systems you look at here. Because of the simplicity of the problem, it is. Now we have the reactive boundary condition. So we have this here, right? And this then means, because the left-hand side is 0, that the reaction must balance on the membrane. So reactive boundary condition means we have minus dc d set c at z equal to 0. This is 0 from the above. And then we have m star, f of m star and c star being 0, meaning the reactions, as I said, balance right at the membrane. What else do we have? We have mass conservation, and that's now easy to read off. Here we have m star, it's a constant, times L, plus here h times c star is the right-hand side. So our mass conservation becomes of the simple form m star over h plus c star equals to n bar. Right, so it's a simple, completely uniform base state that we have in our system. Next is that we linearize around the base state, so around our homogeneous steady state. And for that, as usual, we just write for C, this is our homogeneous steady state, plus some kind of perturbation. And we also write for m of x and t is m star plus a delta m of x and t. And we want to focus now on the theory of these perturbations because we want to learn how are they growing over time when I look at the equation of motion. So let's now look back here at the left-hand side. These are our two equations of motion. These are our boundary conditions. This is our reactive boundary conditions. What I have to do is I have to insert my linearization ansatz right here and at all the boundary conditions. You see here on the left-hand side where you have a diffusion, time derivative, the constant term cancels out. Here on the right-hand side, because my base state is spatially uniform, also m star and c star are not there. You have just delta m. And here I need to expand the reaction term in powers of the deviations of delta m and delta c, noting that f at 0 is 0 because I'm expanding around the steady state, okay, where I had this to be 0. And the same I need to do for the boundary conditions. So let us write this out. We have the time derivative of the perturbation in the cytosolic concentration is just dc Laplacian in this deviation. For the membrane concentration, the perturbation of that, same thing. I do have dm dx squared delta m, and from the reactions, I need to expand around the fixed point, and there I do have these functions f, m, and c, and they are defined as the partial derivatives with respect to dm or c evaluated at the fixed points. For the boundary conditions that are no flux boundary conditions, I don't need to worry because, well, they're just the same. Nothing really changes. the M stars and C stars cancel. So let's look at the boundary condition for the reactions. And for that, I get the perturbation in the cytosolic flux at z equal to 0. Okay, this is equal to the same expression as we had here, but just with a minus sign, minus Fm delta M minus Fc delta C. And of course, the delta C here needs to be evaluated at the membrane. And the same, of course, there as well, because I'm looking at the dynamics, which is the dynamics for the membrane. Good, I don't write out the boundary conditions here because they're the very same. I don't have to copy that. And now we need to make an ansatz to figure out what the solution to these differential equations with the boundary conditions are. We have a finite domain between 0 and L with no flux boundary condition. So we can expand in trigonometric functions. And because of the no flux boundary condition, the only trigonometric functions that are relevant are the cosines. So for delta C of x and c and t, we have some amplitude that I call delta C hat. And then I have a cosine qx as a possible basis set for the solutions in the x direction. The same, there comes more, but I'm writing this here now for the moment. This is an amplitude delta m hat, also times the cosine of qx. Then I also want the time dependence, and there you go about as we had it. We make an ansatz of an exponential function. So we have a growth term, growth factor, e to the sigma t. And we do have this for both m and c. And now I'm done with m, but I'm not done with c. This here can, in general, also have a profile. We found that the steady-state solution doesn't have a profile. But the perturbation, of course, can have a profile. So I need to be careful here and add a profile function that in general depends on z and can also be a function of the wave vector and the eigenvalue. That I call profile function for the cytosolic density above the membrane. All right, so we know the Q's, right? The QNs that are allowed for that need to respect the corresponding boundary condition, no flux at the ends, and that selects a finite set of Fourier components that meet that requirement. So you can only have multiples of pi divided by the system length with n equals 0, 1, 2. So all the integers, positive integers, including the 0. That's the only solution for the eigenvalue problem along the box direction. What's more tricky now is really to what is the profile function, this one here. How do I get a corresponding equation for that? Well, we have all the equations on the board, so we just need to work it out, insert the ansatz that we made here into our linearized equations of motion, and then get for the equation for the profile. So the profile as a function of z, and also in a parametric way depending on sigma and q. that's inserting here in the first equation for the cytosol. This is equal to a minus dc times the wave vector squared, again the function c, and I do have plus dc dz squared z, right? So we still have a differential equation in the z coordinate that we need to solve. So let's rewrite this equation and put things on two different sides. So let's put the differential operator on one side, and on the right-hand side all the rest. So that would be q squared, and dividing by dc plus the growth rate divided by dc times the function z. Okay? And that object here that I define as kappa squared as a shorthand. Good. Now, when you want to solve that equation, we had this yesterday in our class. This is an equation that's solved by hyperbolic cosine and hyperbolic sine. So, in general, Z will be a linear combination of a hyperbolic sine, cosine, and a hyperbolic sine. Okay, and I use the freedom that I have in shifting the argument such that I'm obeying the proper boundary conditions. Okay, so I have this as kappa h minus z, and this here also as kappa h minus z. We have another boundary condition, dz z at the ceiling, so at h is equal to 0. And then if you read that and do the derivative, you will see that's only possible if the second parameter b is equal to 0. So b needs to be equal to 0, and that's the only solution that I have that obeys the proper boundary condition is the hyperbolic sine. Now let's normalize it, and there's a choice to make, right? Because when you look here at the right-hand side, we have an amplitude here already, and we can account for the amplitude by this factor delta c hat. And then we can conveniently choose the amplitude of z as we like it. And I wanted to choose that the amplitude of this is equal to 1, and that fixes the constant a. So we choose z at the membrane, so at 0, we choose that to be 1. And then our profile function as a function of z and a function of these parameters, sigma and q, is the hyperbolic cosine of kappa h minus z divided by the corresponding expression that you get when you put here z equal to 0, so kappa times h. And note that this dependence on sigma q that we have here is contained in this right-hand side expression through the value of kappa, because kappa, this object here, is a function of my eigenvalue and of the corresponding eigenvector q that you have. Good. Now we can define an object that we need later. It's the slope of that. So we call this the bulk surface coupling coefficient, and I call it gamma. So I define gamma as a function of sigma and q to be the gradient of that function z at the membrane. So at z equal to 0. And this is, when you do the math, minus kappa as a function of sigma and q, hyperbolic tangent of kappa of sigma and q times h. All right, so now we are almost done. We can now use our ansatz that we have, right? This whole expression that we have here, and insert it into the linearized equations. And then we get the corresponding eigenvalue and eigenvector relation for the problem that we want to study. So let's just collect the terms that we have. So when you insert that, what you get is for the dependence of delta C times gamma of sigma and q minus Fc minus Fm. Here we get Fc, and here we get minus sigma minus q squared dm plus Fm delta C hat delta m hat equal to 0. That is our eigenvalue problem. And as you have seen now, this dependence that we have here that comes in through the profile function makes this a non-trivial problem to study. Right? So this here we call L of sigma and q. That's our linear operator. And the condition for a solution is the characteristic equation sigma q q. The determinant of that has to be 0. And that is a generalization of the usual eigenvalue problem to a form that we had yesterday. Right? This is no longer a linear algebra problem that you have to solve. It's a problem which involves the nonlinear dependence of the problem on sigma and q through this object, which is the slope of the profile equation right at the membrane. Okay. Good. I'm not going further in doing the analysis here. This is now a computational problem where you just have to solve that equation, and then you get the corresponding eigenvalues out of it. But I stop here and just show you how this works in principle. Questions? Yeah?
So, like, some of these goal is to see, for example, at which z profile then it will be unstable. Like the prediction on this homogeneous state will be unstable. It depends on the profile.
No. The profile is something you get out. So you start from a steady state, our base state, and we found by doing the calculation using the boundary conditions that the base state is uniform on the membrane and it's uniform in the bulk. We have an M star and C star. They're given by the Nark-Klein and the mass conservation condition. Now I'm asking, when I have a perturbation of that homogeneous steady state, what will this perturbation look like? And the answer is pretty much as we had it, that in the x direction, you will have Fourier modes that develop. And which one of the Fourier modes in the box direction is the most dominant depends on the shape of the dispersion relation that you get. So you start from something which is small and 0 first, because e to the sigma at time equal to 0 is just a small perturbation. And then, once you have a perturbation that develops, it will have to have a profile along the cytosol in the z direction that is given by the solution to the profile equation. Okay, so it will have a hyperbolic cosine solution. Right? It's an emergent property of the perturbations in the system. Other questions? All right, then let's have a, yeah, come on.
And this cosine emerges only when we assume like the original homogeneous state is uniform along x. So it's...
No, I'm not really assuming that. It's the outcome. Okay, I say, let's say it's m star. But I can also check that this is a solution, right? It's a unique solution. It's the solution of the homogeneous steady state, the only one that I have.
Yeah, but I mean, because...
There is no other steady state solution.
But in the, like when we consider cutting that into bar, we indeed got the profile along Z. But now
we don't mix things up. So yesterday, we had a cytosol, and we had an active and an inactive component. And for the active and inactive component, each one of them had a profile. The total of them didn't have a profile. And now I'm looking at a situation where I no longer have switching between inactive and active states. So, right, this is just one cytosolic component. And for that case, the homogeneous steady state is uniform in z direction. Okay, I can also make the problem more complicated. I could say, let's start from a system, which I don't have on the board anymore, where I have two cytosolic components, an active and an inactive one, and I do have a single membrane component. Then the steady state from which I start out with is already non-uniform, as we showed yesterday. And then the analysis is even more intricate than the analysis that I do here. Clear now? Okay. Good, then let's have a break.